So, now coming into the high assurance boot. So, we will have to understand that high assurance boot is basically a boot sequence to ensure that the authentic software is being used. Now, what do we mean by authentic software? When I ship out a device from the factory, right, I have actually tested a particular version of the software, a particular image to be used in that particular device, right. As long as my customer is actually making use of that same image, I am perfectly okay, because that image is fully tested, found to be secure. So, when a customer is using that image, I am okay with it, right. But there is also a possibility that a customer could have got compromised and somebody could have actually made use of, dumped another image or trying to give it a new image which is not matching with whatever I had shipped the device out with, right. I have to catch that kind of situations and refuse to boot, refuse to boot up in those kind of scenarios, right. So, that is basically what is referred to as high assurance boot. So, establishes a known good system date. So, high assurance boot protects against platform repurposing. So, platform repurposing here in the sense I have actually shipped the device with a particular platform with a particular image, somebody is actually trying to replatform that, replatform in the sense they are trying to modify that particular image in an unauthenticated manner, which I do not want to accept and allow booting up in that kind of a scenario. So, rootkits and similar unauthorized software designed to harvest secrets, circumvent access control. So, this is an example that I gave you, right. So, somebody puts in a modified executable, I run the executable, but that executable is compromised, it is doing the job what it is supposed to do, but in addition to that it is also doing some other security violated jobs also, right. Offline software reverse engineering, all these to be prevented with, right. Now, this is just a summary slide of how the whole thing is actually working. Okay. Now, what I will actually do is, this is my processor, I have mentioned that there is something called as a fuse. Okay. So, I am going to dump some value inside that fuse. This is a one time activity, that is why we call it as OTP, one time programmable, right. So, I am going to fuse some value inside, I will tell you what the value is. Now, come on this side, this is basically my image building and image generation part. So, this is my software image. So, let us say this is a U-boot. What is a U-boot? Have you heard of U-boot? It is a bootloader. So, we told from boot ROM, the next thing will be the bootloader, the bootloader will be to the OS, OS to the root file system, right. So, the bootloader, let us say that this is one image that I actually have which I want to protect, because the HAB needs to start protecting right from the bootloader, right, because the bootloader image also I can download it over the any of the peripheral. So, I need a protection on that particular bootloader image, right. So, if this is basically the software image that I want to protect, any image that I want to protect, I generate a hash value for it, hash we already know, correct. That is the reason why I talked about all that in the morning before lunch, right. This hash value I basically sign. What I sign with? I sign with RSA algorithm, right. So, I use a private key and then sign, right. So, this sign value with the image, I basically generate a signature and this complete portion is flashed. So, when I say flashed, we essentially mean that it is now dumped into my on device storage area. So, it can be a NOR flash, NAND flash, eMMC, whatever. So, I have different kinds of media that is there, any of the stuff that this particular device is supporting, I can dump it on that, right. Now, this is actually available here, which is basically a signed software image, right. Now, I am powering it up. The whole concept of security of this high assurance boot, what we are talking of is, I want to verify on a power up that whatever I have actually given is the one that is actually right now trying to get booted up with, that is a requirement, right. So, now when I power up, I basically have the image with the signature concatenated together, correct. Now, with the signature, the image, I basically split it up into two parts, right. On the signature, which is basically encrypted with my private key, I have to use the public key, right. So, I use the public key from the header portion that has actually got added here, right, but there is a possibility that this also would have got tampered with by the person who is trying to spoof, right. Now, how do I verify that? I take the public key out of that, and I told I would have actually got some value fused here, right, which is not readable by somebody outside. That value is basically a hash value of my public key that is there as part of this generation, right. Now, when I extract the public key out of that, I have the hash value of the public key generated and compare it with the hash value that is fused inside. If they are same, I use that public key and decrypt the sign. Okay. Now, I get back the hash value that was encrypted as part of the generation. Now, I have the software image, I send the software image to the same hash algorithm, right. Now, I have got a generated hash, compare these two hashes, only after these two are same, it essentially means that there has been no modification on the software image. Okay. So, nobody could have actually modified the public key, because if they have modified the public key and then put it, this verification would have failed, right. The verification of the hash of the public key with whatever has been fused inside the processor, that verification would have failed, right. Once that verification is successful, I use that public key and compare it with the hash value that has actually been generated out of this, do this comparison, only if both of the same, I load the software image and then run it. If they are not same, I basically do a abort, right. This entire process is a high assurance boot, right. So, this is just a summary, we will actually take a little detailed look at this subsequently. So, what are these enablement tools that are required? I need something like a code signing tool, right. So, this code signing tool is basically going to generate my digital signature and then going to do the signing of the keys and signatures generated by the device manufacturer. So, this entire part I use a code signing tool that Freescale is actually providing, right. So, with this part I will be able to do the signing, I will be able to build up this concatenated image all in one shot. I just run one command, right. I generate the keys, I edit some files, after those files are edited I run a command as part of this code signing tool, this entire concatenated image with my original executable contents with the signature all will be generated, and that I basically flash it onto my device. Now, what do I use for flashing it onto my device? That is used for my manufacturing tool, right. So, this manufacturing tool will basically flash the signed image that my CST tool has.
Excuse me, sir.
Yeah.
Sir, this Pratik Pandey from Anurag. Actually, sir, I have doubt on this previous slide.
Okay.
When this high boot is taking place, the software image that we are signing on the first side, is that image containing bootloader also?
Okay. See.
Operating system part?
Okay. So, there is something called as a chain of trust, right. So,
Okay.
in the chain of trust, what we are actually doing here is that, as I was telling you the boot sequence earlier, you have the boot ROM code, you do not suspect that. So, you always believe that the boot ROM code, once it has been written, there is nobody else who can basically go and update that part, and that boot ROM code is basically going to make use of your bootloader. So, the first image that will be authenticated by this high assurance boot, will be the bootloader image. Once the bootloader image is authenticated, like your U-boot for example, because most of these devices today actually use U-boot as a bootloader. Once that bootloader is authenticated by this HAB, the bootloader the U-boot will be made to authenticate my kernel image. So, as long as the kernel image is actually being authenticated by somebody who has already been authenticated before, we are completely okay with it, and this is basically what we refer to as a chain of trust. So, as long as the person who is authenticating is already authenticated earlier, if he has basically telling another image that is coming in the line that yes, this particular image is fine, it is not compromised, and it is successfully authenticated, we can go ahead and believe. So, that is the underlying assumption. So, right up to your kernel image, you can use HAB to authenticate it from your bootloader. So, subsequently for our root file system, what we have actually done is we have done the complete encryption of the root file system, so that even if somebody tries to access the content and then take it out, they will require the key, and that key is actually stored internally as part of our SNVS area. So, with this approach, even though we do not have the root file system authentication to be done directly by HAB, we actually have this via media approach, which is also pretty much equally safe to go ahead and authenticate your root file system also completely.
Sir, we have a question from Care, sir.
Yeah.
Sir, the toolchain that you have shown in the next slide for generating the entire storing the private key and all, and creating this signed code. So, do you consider that toolchain also to be part of your trust chain, or you have some extra verification methodologies through which you have verified those toolchains?
Okay, those tool chains are actually provided by the vendor. So, you are basically referring to this code signing tool and the manufacturing tool, right?
Yes, sir. Next slide.
Yeah, this one right now. Yeah, so these two tool chains are actually provided by the vendor, not in a source code form, but in an executable form.
What's up that trust chain that is being derived out of this code? So
No.
dependency on these tools.
No. The trust chain. No, the trust chain that is actually derived is basically only from the point of view of the boot up sequence.
But my question was, you are signing that code using this toolchain only.
Correct.
If there is some malfunction happens at the time of signing, then the entire procedure which you have shown in the previous slide, will not that have some vulnerability, probable vulnerability, because that depends on the signing process itself.
Yeah, so one is the Freescale is actually providing you this executable in an executable form, and secondly we can actually go ahead and request them to have the source code available to us, so that we can do a formal verification of the code.
So that is there in your plan, in future plan.
Yes, that's right. That's right. So, right now we have actually got a comfort completely on how this whole thing is working. We have implemented it, and we have been able to see it happening on our own device also. So, we are basically going to ask Freescale to provide us the code, so that the code of the CST as well as the manufacturing tool can be done a formal verification and verified that there are no malignancies inside that as well.
And that your estimate about the code size and the properties of the code technologies of manual verification.
Yeah, actually the size of that code as I understand is not very big. So, I guess it should not go beyond a very few thousand lines of code. So, I presume that with the current formal verification methods that we have, we should be able to verify that. It is not like really a very huge thing like around tenth of the 10,000s of lines of code or whatever it is. So, it should be definitely verifiable.
Yes, sir.
So, that is definitely in our plan currently.
Okay, thanks.
Yeah. So basically the manufacturing tool is sort of in charge of trying to go ahead and dump the tool onto the, dump the signed image onto the flash, and also to basically go ahead and write the fuse values inside the appropriate register locations, because remember the fuse values are only modifiable, that is writable only once. So, once you write that values, it is no longer programmable or modifiable. So, that also will be actually getting done as part of the manufacturing tool itself, right. So, this slide basically talks about how the CST tool really works. So, it basically takes a file called as a CSF file, command sequence file, along with the product software. So, on the code signing tool host, these two files are basically given as input to the CST application. It generates the HAB data, which is basically the signed image with the CSF header, what we call as an IVT table, all available as part of the signed image. And then the signed product software is basically what is used by my manufacturing tool to dump it onto the storage media on the device, right. So, yeah, so the very flowchart mechanism of how this whole thing is actually working. So, on a power on reset, the HAB library, if it is configured, is going to come into play. The bootloader image on whatever media that I have basically configured my boot mode register to be is expected to come in. And that will also have the CSF information with all the details on which part of the entire file is my image file, which part of it is basically pertaining to my the sign data and all that stuff, and that is actually going to be used by my boot ROM code with the boot device driver inside. Once that is authenticated by the HAB library to confirm to this particular checks, my bootloader will be getting executed. So, this bootloader will now take up the OS part, which is the next level of authentication, that is the third stage of boot stage, right. So, that is basically what I was telling you, that in this chain of trust we expect and assume that the boot ROM code is pakka, right. So, there has been no compromise on that part, because that is not possible outside of factory to be modifying that. So, on the boot ROM code is actually going to be looking and validating the bootloader. Once the bootloader is validated, the bootloader is now going to take a look at the OS and validate it with the corresponding CSF file. Once that is also validated, now the OS is going to get loaded and then start to get executed, right. So, that basically the chain that it actually will typically happen. So, this is just a slide on how the whole thing is actually working with the CSF. There are different CSF commands that are actually available, which all goes in as part of my header information inside my signed image, right. So, manufacturing tool features, as I told you, image provisioning to boot device. So, uses the serial download protocol of IMX boot ROM, support for fuse burning. So, these are the things that are actually done by the manufacturing tool. So, basically updates the image into the corresponding storage media on the device, and then fuses the values that has to go into the OTP register of my processor, right. So, the XML configuration file is used as an input by my manufacturing tool, and using the serial interface into my IMX6 device, the whole thing is actually dumped onto my device, right. So, the XML file sample XML file will look something like this, right. So, for example, look at it here. These are the commands that are used, the XML commands that are actually used to fuse the values in the corresponding locations, right. So, if I basically write it into this particular file, this particular file is memory mapped into my corresponding OTP register. So, if I echo a value into this file, that will go and get burnt into my particular location, and then I finally do a, once I do the complete verification of this entire fuse values, I basically change the configuration into a closed configuration. So, after which it will work only when I have the authenticated image alone loaded, and it will fail when I do not have the authenticated information. So, all IMX ICs shipped from Prescale in open security configuration. When I say open security, security errors are non-fatal. So, even if I have in the open configuration a non-authenticated image, it will still go through fine without any issues. Terminal configuration for non-secure products, when I really have the device required to be working in a non-secure manner, this will be my final configuration, which I keep it as an open configuration, right. And for secure products, this is development configuration, which I use purely for development, and before I ship it, if the product is to be a secure product, I go ahead and do a closed configuration. So, what is this closed configuration? No code from any boot device is allowed to execute unless successfully authenticated, and boot flow enters the ROM serial mode on failure, waiting for the authenticated image to be coming in over that serial mode, right. Suppose if the image that I have actually stored internally as has not been successfully authenticated, in a closed configuration the boot flow will enter the ROM serial mode to look at, to see if I can have an image coming into that which could be successfully authenticated. So, if there is no image coming in on that also which could be successfully authenticated, then it will just refuse to boot as if the device itself is completely failed, right. So, the way the secure image is actually generated, we just gone through this part right now. So, this is basically the chain of trust that I was actually trying to talk. So, the bootloader getting validated by the ROM code, bootloader then validating the kernel validating the individual applications and so on. On the IMX6 processor with high assurance boot, all the applications right from the root file system, we do not have the inherent capability to do it with HAB itself. So, we are implementing the encryption part of it here to have the trust chain implemented, right. So, this is basically what actually happens. So, the device details parts of it is also fused. As part of my image, I will have the device details also available. So, as the first phase, those will be verified. Once they are successful, my public key part of it will be extracted, the public key verification will happen. So, the hash of this public key and what has been fused earlier as a public key hash will be compared. So, once they are compared, I know that there is I have got the correct public key. I will use that public key and then decrypt the hash that has been available for this system image. So, the decrypted hash value and the hash that I have generated right now on the device for my system image portion, pure system image portion, that comparison will be made. If it is same, the system will be booted. If it is a failure, the device will go with a reset. So, the tamper detection part of it, I have a tamper detect pin that is there. So, that pin is actually exposed out of my processor. That pin basically will have a 1 volt continuously coming in until a tamper event occurs. When a tamper event is occurring, the TMP detect pin will be given the 0 volt, and what needs to be done when it detects the voltage difference is actually configurable. So, whether I have to go ahead and delete certain particular memory areas or certain files, whatever it is, all these are configurable, which I can just configure and then get those things actioned upon whenever a tamper is detected, right. So, the trust architecture as a summary protects assets of multiple stakeholders. So, we saw what those different assets are, and for each of those assets what kind of threats come in. Guards against sophisticated attacks. With the tamper detection, you will be able to detect different kinds of attacks, physical as well, and assures software measures by ensuring that whatever is authenticated image is what is actually getting booted up every time.